Hi all. So today I'm going to be talking about the contravariant and covariant components of a vector. What are they? These concepts are fundamental in the field of differential geometry. Differential geometry has sort of a long history. Probably the first time that it was put to practical use was actually in the problem of land surveying in Germany. Famous mathematician Gauss was given the job of figuring out how you would measure property and boundaries and so on a bumpy Earth surface. So he had to develop how to do calculus on these curved surfaces. It's based on the idea of the distance between 2 points in Euclidean geometry. You know, if you have 2 points separated by some distance c over here, know the sides of the right angle A and B, then the distance between the 2 points P1 to P2 is given by the Pythagorean theorem. And you can sort of imagine taking one of these triangles and shrinking it down to an infinitesimal and putting dx and dy on the sides, and the lengths, the differential lengths, ds squared, sorry, the square is over here, is equal to dx squared plus dy squared. And you use this in calculus to calculate the length of a curve in 2 dimensions, for instance. You can use this little differential formula here. And if you have a bumpy surface, though, or a curved surface, this formula doesn't work. And instead you have to use a sort of a fancier version of it, where you multiply the differentials by a matrix Gij. And this thing has a fancy name. It's called the metric tensor. So R. The metric tensor is telling you how to combine products of these differentials and multiply them by some appropriate factors to get the infinitesimal arc length. Physicists found that it was very useful in understanding the theory of gravitation, and so Einstein's general relativity makes extensive use of differential geometry, and here is Einstein's equation for gravitational field caused by matter density that's moving around with velocities v. These are the components of the vectors v, the velocity vectors. There are actually 4 vectors in relativity, and you have these funny tensors, capital R, Ij, and then scalar R over here, and these are functions of position. And then here's the old metric tensor showing up again. And it turns out these R quantity derived from G. They're functions of G and its derivatives. So this is really, it's one big nonlinear differential equation for solving for Gij. So in general relativity, instead of solving for the Newtonian gravitational field like we do in Newtonian mechanics, and find what the metric tensor Gij is, and that's the unknown quantity in this equation. And it's usually kind of a difficult equation to solve because it's nonlinear and it has a lot of components. For instance, in general relativity, this G is a 4x4 array, so it has 16 components. More recently, differential geometry was used to prove this famous long-standing important problem in topology called the Poincaré conjecture. And you might have heard of this. It was in the news in the last couple of years. And this mathematician, interesting guy, Gregory Perelman, was able to prove this Poincaré conjecture about a sphere embedded in a 4-dimensional space. And he used something called the Ricci flow equation. And that's sort of it's another type of equation where the unknown is the metric tensor, and it's a diffusion equation for this G. And here is an example of a Ricci flow equation where G is the metric tensor, and this Rij is called the Ricci tensor. Let's see if I've got it written down here. Rij, named after another mathematician. Ricci tensor. It's also called the Ricci curvature tensor sometimes. So, turns out that differential geometry has very useful over the years, and it looks like it's getting wider and wider applications. So, fundamental to differential geometry is the concept of covariant and contravariant components of a vector. And so let's take a look at the next page now and look at the variant and covariant components of a vector in kind of the simplest situation, where you have a Euclidean flat plane and you have a physical object that you're kind of representing. Say a surface of a table, and you've put a ruler down on the table, so it's an actual physical object, and you move it around, and then maybe you draw some coordinates, x and y, Cartesian coordinates, and you want to get some numbers for the length of this object in this coordinate system, the x and y coordinate system. The idea is that you have some real physical object represented by this vector c, and the coordinate system is just a way of labeling the endpoints of the vector and giving you a quantitative description of it. Put the origin at one end of the vector of this meter stick, let's say, and then measure out the distance along x axis over here, and drop this perpendicular down to the axis, and then call that cx, the x component of the vector c, and dropping a straight line parallel to the x-axis over here until it hits the y-axis, and then this value of y is cy, y component of the vector. And so you can describe this particular point here as an ordered pair of numbers, cx and cy. These are the Cartesian components of c. And now let me get my pen going over here. So the idea of the length of a vector, well, one thing about it is that no matter what your coordinate system, the length of a meter stick better come out to be 1 meter. And so there's a formula for the length of c. It's the Pythagorean theorem. So this length of c is equal to the sum of the squares of the two components, cx and cy, and the square root of that gives you the length. So we're making use of the Pythagorean theorem here to get this formula right here for the length of c. What would happen if we used a different set of coordinates? And I'm going to choose one that's a little bit tricky. Instead of Cartesian xy coordinates, I'm going to use a set of coordinates here, u and v, but instead of having the coordinate axes meet at a right angle, they're going to meet at some oblique angle, alpha. The u and v then can be called oblique coordinates. So in this coordinate system here, in u and v, what then are the components of the vector c? So we'll go to the next page.